more likely to be found on the payload and not on the header. There will not be header misuse on the communication. The most famous anomaly detection system based on the payload analysis is PAIL, that was developed by Salvatore Stolfo and his research group. We started from the PAIL algorithm to improve it, and we built Poseidon, that stands for Pale over Sum for intrusion detection. We actually added another tier before the PAIL algorithm. We built a two-tier architecture for anomaly detection by introducing self-organizing maps. And we found out that this approach increased the ability to find anomalies of PAIL. PAIL works with models, and each model is classified by the IP address, network IP address, the destination service port, and the payload length. And given its nature of statistical approach, PAIL needs a training phase before starting. So during the training phase, those models are computed, and for each model, some statistical values are stored. Then, in the detection phase, for each observed payload, it is compared the byte frequency distribution of this payload with the statistical values of the associated model, and the Mahalanobis distance is calculated. And if such distance exceeds a given threshold, then this observed sample is classified as an anomaly, so as a possible attack. Unfortunately, PAIL has some weaknesses, and one of the weaknesses is that it is prone to mimicry attacks, because it inspects the byte frequency distribution, and for attackers it is possible to craft attack packets by padding some characters in order to make the packet seem to be normal, to have a normal byte frequency distribution. And another bigger problem of PAIL is about the misclassification of the models, because the payload length parameters is not suitable for classifying models. As an example, we can say that if we would have to classify fruits, and we use the weight as a parameter for the classification, we could see that a big apple and a banana having the same weight being actually two different fruits, while using a different parameter such as the shape, it would be different, because an apple and a banana, whatever the weight, would be classified in two different models. And this is the case for PAIL, because two different payloads, two payloads being quite the same payload, but having a small difference in the payload length, will be split in two different clusters, in two different models, and this is not a good classification. So what can be done to improve PAIL? We need another parameter different from the payload length in order to build the models, and this parameter must take into account the whole payload information. We want the classification algorithm work in an unsupervised manner, and we want that similar payloads are classified in the same class, and different payloads are split into two different classes. So this is a typical clustering problem. So we focused on different clustering algorithms, trying the most popular ones, such as k-mean, k-medoids. But the one having the best results was the self-organizing map. That is a neural network, a single-layer neural network that is suitable for classifying high-dimensional data, such as the payload of the packet that is high-dimensional data. The self-organizing map to work, to perform the classification needs a training phase, an initialization and a training phase. During initialization, a number of parameters must be set, and these parameters then influence the behavior of the classification. Then, during the training, a training set can be used to train the network and to make the network able to do the classification. And an important feature of the self-organizing map is that the classification it provides helps in avoiding mimicry attacks. And this is because we use two different approaches during the first step and the second step. During the first step, we compare the payloads by its byte value, byte per byte, while in the pale algorithm, we compare the byte frequency distribution. So it's much more difficult for an attacker to craft a payload with the pad characters in order to make the packet seem normal for both the two levels, and this helps in avoiding mimicry attacks. So the whole architecture of Poseidon is presented here. We have a new tier, a new level that is composed by the self-organizing map that provides the classification. The self-organizing map needs a training phase. So first we have to train the first level, and then we can use the classification for the pale algorithm. First for training the pale algorithm, and then for detection. So two different training phases are needed. But it is important to note that for updates, so when the network environment changes, if the amount of the change is small, we can only retrain pale models without retraining the self-organizing map. While for biggest changes on the network environment, we need actually retrain both the levels. We benchmarked Poseidon with respect of pale on the same data set that is the DARPA 1999 data set, is a standard data set. The same data set that was used by the pale crew. We applied the same restriction as the pale crew in order to compare the results. And here in this graph, in these charts, you can see in the blue line is about Poseidon, and the green line is about pale, and the red line is about our experiment we did with pale, because the information about the detection rate with pale, we extracted this information from the pale paper, and then we wanted a confirm of this data, so we repeated the pale tests ourselves, and we can see that Poseidon overcomes pale on every benchmark protocol, and in particular we can see that for HTTP traffic we have the best results, having 100% detection rate with about 0% false positive rates. So Poseidon is not suitable only for output anomaly detection, but also as a standalone network intrusion detection system, anomaly based.
Okay, let's have now finally put all together to get what Aphrodite can do. In this picture you can see the general architecture of our solution, and in the upper part of the image you can see that there is an input NIDS analyzing all the traffic that is incoming in our network. This is the most common, I mean, the normal configuration that we have. So this needs is not immediately forwarding every kind of alert to the IT personnel, but it's, instead of doing that, it's forwarding a proto alert. So it's not ready, no, it's not confirmed yet that this is an alert, and it's forwarding this inside the Aphrodite architecture. What happened is that we have our web farm, for example, on the right, and so Aphrodite is waiting for the web server or any kind of services that is monitored to produce the output. So when the output will be finally sent to the user or to the supposed attacker, our output anomaly detector will analyze it. In this case, we want to stress that the input needs can be any kind of intrusion detection system, so being signature-based or anomaly-based, this doesn't really matter right now. But the output anomaly detector, as the name said, it's Poseidon, so it's our anomaly detection-based system. So the output anomaly detector inspects the payload, and finally it produces this anomaly score, and if this anomaly score is exceeding a given threshold, the correlation engine will finally produce the alerts. If this is not happening, so this threshold is not exceeded, then the alert will be considered as a false positive, and the IT personnel will not be disturbed by this activity. And then the traffic will flows normally out of our network. So let's now have a closer look to what's really happening inside. So the correlation engine receives the proto alert from the intrusion detection system monitoring the input, and it starts to track the connection. Right now we are talking about TCP data flows because, well, we could consider UDP, ICMP, but nowadays almost all the traffic that we see on the internet and that we are interested in protecting is something going on TCP. So we're talking about TCP connection and TCP streams. So the TCP connection is marked by the correlation engine, and since that moment the correlation engine is waiting for the output anomaly detector for this kind of response. Then, as I said before, if the threshold has been exceeded, then the alert will be really forwarded by the correlation engine to the IT personnel. But there are some exceptions. Like, for example, when we said before, if the attacker is aiming to generate a denial of service, then we will not see any kind of response, so we cannot analyze anything. So the correlation engine has to wait a certain amount of time, so we can say 1 minute or 30 seconds. Nowadays I would wait 10 seconds, but if you really want to be sure, 1 minute is okay. And if the output is missing, then this is considered in any case an attack that has taken place and that the system is down. Then we have other two exceptions that are related. Let's say that if the input network intrusion detection system that we are using, that we put inside the architecture is an anomaly based, then we can use other information to enforce the idea that what is happening is really an attack and is not a false positive. So we can use, for example, the anomaly score given